Welcome, greetings everyone. Welcome to the Topological Complexity Seminar hosted by the AATRN group. And today we're having Nick Wawrykow from the University of Chicago, who will speak on the disconfiguration spaces and topological complexity. Please go ahead, Nick.
Great, thank you, Jesus. So I guess for me, topological complexity is something I really only got introduced to a few months ago. So for me, I probably have a little bit of a basic understanding of it. But to me, topological complexity is something saying, how hard is it to motion plan in a space? And throughout all of this, my spaces will be X, and I will use F sub n of X to denote the nth ordered configuration space of points in X. So this is just going to be the space of ways of embedding n labeled points in X such that, well, our points don't overlap. Right. Nth ordered configuration space. And well, this family of spaces has been one of, like, in my opinion, the richest things to study, or at least earliest things to study for topological complexity, because motion planning can be described rather straightforward, saying, okay, you've got 2 points in your configuration space. So say you had 2 points in the ordered configuration space of 3 points in the plane. So 1, 2, and 3. And this is a point in the ordered configuration space of 3 points in R2, so points in X. And right, motion planning or topological complexity is saying, okay, if we want to go from this point to, say, the point where 3 and 2 are switched, we'd have some algorithm to do this. But if I say perturbed my endpoints or my beginning points a little bit, well, I'd want to have a similar algorithm to go between these points, but unfortunately, because this space isn't contractible, well, we can't do this with a single operation. And right, we need to break up our space, in this case, the ordered configuration space up, into different regions where we each have a motion planner on each of them, and say, okay, with this in mind, right, we can now say, okay, here's an algorithm saying, choose your start and your endpoints. You have a nice path in that space. And as long as you can break your space up in this way, or you break your space up into enough nice regions, this motion planning problem is solvable. So, right, for me, the question is going to be, right, how do we motion plan in these configuration spaces? So question, how do we motion plan in these ordered configuration spaces? And right, I'm going to set my convention of saying we're going to be using reduced topological complexity or reduced sequential topological complexity. So convention, right, y sub I is going to be equal to the path space of y. Pi sub r is going to be the map from y sub I to r copies of y. And right, this map is going to say take a path, gamma, and it's going to send it to its points and the intermediate points in between, where our points are evenly going to be spaced out. So we've got gamma 1 over r minus 1, all the way through gamma r minus 2 over r minus 1, gamma 1. And right, what is the topological complexity or the sequential topological complexity of this? Well, we're going to say the rth sequential topological complexity of y is going to be then the minimum k, so min value, such that there exists u0 through uk in y, the r copies of y that are open, cover this space, and such that we're going to be able to have continuous sections s sub I from u sub I back into the path space that are continuous sections of pi, sections of pi sub r. And right, if r is equal to 2, this is the classical topological complexity of Farber, whereas this definition is kind of a little bit of a bastardization of Rudyak's original definition, but it appears in that paper. And right, all we're saying is, okay, we've got our space over here, y, and we want to say, okay, let's move between two different points in our space, and we're going to make, in this case, r minus 2 stops along the way. Well, how many different ways do you have to break up your region so you can have a continuous path on each of these spaces? So, right, let's work out some nice examples. So first example, slash theorem, and this is in some of the earliest papers of Farber, and this is with Jasvinsky, is that, well, if we're dealing with the ordered configuration space of points in the plane, then the topological complexity in this case is going to be 2n minus 3. So the second sequential topological complexity, or just the classical topological complexity of n points in the plane, this is going to be equal to 2n minus 3. And just kind of as a sanity check, we can check, okay, does this hold when n equals 2? And when n equals 2, it turns out that the ordered configuration space of 2 points in the plane is homotopy equivalent to S1. And this homotopy equivalence comes from noting, okay, you can fix your first point 1 to be at the origin, and then noting, okay, the only other thing that the second point can do is move around that point like this, and we can scale this so it always occurs at distance 1 from the origin. So, right, we're going to be able to see, oh yeah, this second ordered configuration space of 2 points in R2 is going to look like 1 point fixed with a point 2 orbiting it, and right, that's just a circle. And right, one of the earliest computations in the original paper, Farber is saying, okay, yeah, topological complexity of the circle is going to be equal to 1. He writes it as 2, but he does this non-reduced version. And so we just want to say, okay, in the simplest case, this makes sense. And originally, these results, I believe, were written in terms of hyperplane complements. I'm not going to think of it this way, but it is a nice way to start off with. And we can say, okay, what about a little bit more generally? Well, we were talking about sequential topological complexity, and it's a result of Grant and Gonzalez in 15, that, well, this result generalizes kind of nicely, and we could say, oh yeah, the rth sequential topological complexity of the ordered configuration space of n points in the plane, this is going to be equal to r times n minus 1 minus 1. And the results are a bit more general than this. They consider both planes, larger Euclidean spaces, and things when you have punctures. But for us, we're just going to consider the plane in this case. And we can see, right, okay, if r is equal to 2, we recover the result of Farber and Jasvinsky. So we know these results. But one of the things about the ordered configuration space of, say, points is sometimes it's not realistic. And right, at least for me, a large part of getting into this was kind of, not Abrams, was an argument, was a paper, I can't remember the author, about finding topology in a warehouse. And right, in a warehouse, we could say, okay, we have robots moving around the floor. And well, if we have enough robots, they're all of a sudden going to start bumping into each other, right? If you fill a room with a few dozen ants, they're not going to really bump into each other because they have a lot of space. If you look at the room you're in and you fill it with Roombas, they're all going to start bumping into each other as soon as you have enough Roombas. And so we want to say, okay, let's replace this ordered configuration space of points with something where the points actually take up a bit of volume. And so idea is, well, points are sometimes unrealistic, realistic, and we're going to replace points with disks. And this is going to have the result of replacing the ordered configuration space of points in X with the ordered configuration space of unit diameter disks in X, which we're going to denote by d f sub n of x comma g. And right, we're including this g here because, well, I want to include a metric because we want to consider various possible things that go on. And right, what are these things? Well, just like the ordered configuration space of points, they're going to be an n tuple of points. And now we're going to insist on two conditions. Well, we want to have a generalization of the first the condition for ordered configuration spaces of points, in that we don't want the points to be the same. Well, in this case, we're replacing that by saying, okay, these points, these x1 through xn, they're going to correspond to the center of our disks, and we're going to want the center of our disks to be at least one apart. And also, the second condition is, well, we actually want these disks to fit in our space. So we're going to say the ball of radius 1/2 around each of these disks is actually going to be contained in X. And so this is going to denote the ordered configuration space of n unit diameter disks in X. So ordered configuration space of unit diameter disks in X, I guess X comma G, configuration space of n of these disks. And so, right, let's start thinking about a few of these examples. And the easiest example of this type of space is, well, to say, okay, let's just make our space the plane again. And let's just insist on using the general Euclidean metric. So D2 here. And in this case, right, well, no longer do we just have points in our plane, but right, we now have disks sitting in our plane as such. And if we think about this for a few seconds, we're going to realize, okay, at least in this case, the disk configuration space is going to be actually homotopy equivalent to the point configuration space. And there are a few different ways of doing this. One, you could kind of just say, okay, let's look at our disk configuration space and zoom way back. If we're sitting above our disk configuration space several hundred feet on the ground and we're looking at this on a piece of paper, well, I can't tell you the difference between a disk and a point. And so we'd say, oh yeah, this is clearly going to be the configuration space of points in the plane. The other idea is saying, okay, well, this disk configuration space is going to sit nicely inside the ordered configuration space. And it turns out that this inclusion of disk configuration space into point configuration space is going to be a deformation retract. And how do we do this? Well, given a point in ordered configuration space of points in the plane, we just consider each of the endpoints as minuscule balloons that we slowly inflate so that they have radius 1 in the end. Yeah, they might bunch up against each other, but because we're looking at the plane, these balloons are going to have regions to expand and push out against each other, where eventually we're going to be able to find a point in disk configuration space and be nice and happy and find our deformation retract. So inflate points is the rough idea. So this example, right, nothing new is here. The next obvious example is saying, okay, what's the easiest space we can think about? Well, the plane, and right, we want a little bit of a simplification of the plane. And we could say, okay, let's replace the plane now with a p by q rectangle, which we're going to call rp times q. And we're now going to have the Chebyshev metric or the L infinity metric here. And so, right, p by q rectangle. And right, this is now going to give us something that looks like squares in a rectangle. And this space is something that a couple of years ago, Matt Kill came and gave a talk in the seminar and did a great job of explaining everything that's going on here. And well, there's definitely been some advances in that time, but the still rough idea is we don't actually know everything we'd like to know. And so if you want a little bit more information about this, there's papers by Alpert, Kale, and McPherson, as well as Alpert, Bauer, Kale, McPherson, and Spendlove that talk about this space in great detail. And so one final thing I want to say about this is we're not quite at the point where we can say anything about topological complexity of this space because, well, we don't even know the homotopy dimension of the space. This space is kind of mysterious, and right, we know, okay, the homotopy dimension is at most P over Q over 3, but this 3 here should probably be replaced with a 4, but we need to figure out an argument to do that. And so this is something that I think is hopefully not too far off in the future. And I'll come back to this a little bit, but say Matt has some good reasons to say if you could show this, you could actually find the topological complexity. So we've got a space that's nice and interesting, but it's a little bit too complex for us at the moment. And so we say, what can we do in between these two things? Well, it turns out because we're having now 2 boundary conditions, both smashing vertically and horizontally, we just kind of have made our space a little bit too contained. And if we insist on only having one of these, we're actually going to be able to say quite a bit. So our final example, and the thing we're going to work with today, is when our space x comma g is going to be the infinite strip of width w with the D2 metric. So infinite strip of width w. And right, an example of this is say, okay, let's have our width here be 2. And here's a nice point in our disk configuration space. And so note, so D order configuration space of 3 disks of unit diameter in the infinite strip of width W here. And so, right, one thing to note, unlike configuration spaces of points, this disk configuration space, well connected, you actually have to move some of the other disks around to actually move, say, our disk 1 from this side of the strip to the other, right? We can't just say, oh, there's a nice path that goes from here all the way over to here. Well, this isn't possible without 2 and 3 moving. If we were just dealing with points here, of course, 1 could avoid 2 and 3. And right, this is kind of one of these more constrained real world scenarios we were hoping to consider, right? We could say, okay, what's a nice example of this? Well, say you have a warehouse with a long aisle and you've got a bunch of robots taking things off of the shelves. Well, you don't want the robots to bump into the aisles, knocking everything over, and you don't want the robots to bump into each other. So we say, okay, this example, right, is kind of that. We've got a bunch of robots in an aisle, they're going to take up some space. And well, if you want to be efficient, you probably are going to have more robots than just the width of the aisle here, because we can program such a thing. And so one thing to note here, and this isn't quite clear from this picture, but we'll describe it more in a bit, is that, well, if n is bigger than w, the ordered configuration space of these unit diameter disks in the strip, this is not going to be homotopy equivalent to the ordered configuration space of points in the plane. These are 2 different spaces, and right, it turns out on the one hand, you could view this disk configuration space as being significantly more complex. On the other hand, it turns out the configuration space of the points will have a much higher topological complexity. So let's get to my main theorem for the day, or result, is that, well, if we've got this disk configuration space and n is bigger than w, then the rth sequential topological complexity of the ordered configuration space of n disks in the infinite strip of width w, this is going to be equal to r times n minus the ceiling of n over w. And so when I originally wrote up this result, I wrote this with r equal 2, and I did this via a coupling result. But thanks to Jesus, I started actually thinking a little bit more about sequential topological complexity, and I came along an argument that I'm going to talk about today that allows me to get R very easily and doesn't actually make us think about any cohomology products. Instead, we're going to be able to nicely look at some tori in these configuration spaces. So, right, how does the argument work? Well, in order to do this, we want to actually understand what these configuration spaces look like in general. And well, we want to know what does the ordered configuration space of disks in the infinite strip look like. And in order to do this, we're actually going to start off by asking, what does the ordered configuration space of points in the plane look like? What does this look like? And well, there are a lot of different ways of saying this. You could do this as hyperplane arrangements. You could think of this as the Bray group. It turns out for me, I'd say the easiest way of doing this is to look at the operatic structure. And we're going to note here that the homology of the ordered configuration space of points in the plane is an E2 algebra, E2 operad. And right, the main idea is going back to one of our original pictures, is that, well, we have this class in homology where point 2 orbits point 1. And we know that this is not going to be 0 in the first homology of this space. And we have two rough operations on this. First, we could say, okay, let's replace our point 1 with the pair 1 and 2, and 2 with the pair 3. And this is kind of like a composition of functions. So we're going to now get a class that looks like 2 orbiting 1. And then independently, we're going to have now 3 orbiting this orbiting pair. And I'm going to claim, okay, this is a class now in H2 of the ordered configuration space of 3 points in R2. And we're going to note that this is going to correspond to a 2 torus. So this is a 2 torus here. And right, how do we see this? Well, we've got an S1 factor for 2 going around 1. And we get another independent S1 factor because 3 is going to be independently orbiting that orbiting pair. And it turns out we can't contract either of these things, so we're going to get a nice 2 torus in configuration space. And if we think about this, right, we can just repeat this operation over and over again in the ordered configuration space of points in the plane. We're going to have one more operation that's also going to look like multiplication a little bit. And this operation is going to say, okay, we're going to take 2 of these tori and multiply them together. And so one example, we can have 1 over here, 2 orbiting this, and now we could say have 3 over here. And right, this is also going to be a class in the first homology of the ordered configuration space of now 3 points in the plane. And right, this is because 2 is orbiting 1. We can't contract the loop around of 2 going around 1 because at some point this path 2 would have to go through 1, and that's a bad thing. And similarly, because 3 is far enough away from 2 and 1, it's not doing anything, so it's not going to interact with the topology coming from this loop. And so this map over here is going to be a stabilization map. And there's a lot known studying these various stabilization maps. If we take the unordered configuration space, this is going to introduce the homological stability results of McDuff and Siegel way back from the 70s, I think. And if you take ordered configuration space, well, this is going to give you some stabilization maps that lead to representation stability, which is something that was studied a lot by Farb and his students like Tom Church in the early 2000 teens. So, right, what is the difference between these spaces, right, which are going to give us tori and product of tori, 1 tori product? And what happens with these things when we go into disk configuration spaces? So, right, how about the disk configuration space of n disks in the infinite strip with W? Well, the first thing to note is if our strip is wide enough, we can't do this first operation always, right? If I have disk 1 and disk 2 orbiting, that's perfectly fine. We could fit this inside a circle and just kind of rotate the circle counterclockwise twice, and we'd end up, or counterclockwise once, and we'd end up with this class where 1 orbits 2. And then we could similarly fit 3 over here and now have this class in H2, but right, we run into an issue. I can't fit the circle of diameter 3 inside the infinite strip of width 2. So not all of these classes are going to exist. So that's the first thing to note. The second thing to note, so right, we're saying the first thing to note is, well, these classes aren't all there. The second thing to note is, well, in this case, we're actually going to have a difference of order is going to matter. So if I have disk 1 and disk 2 orbiting like this over here, and disk 3 sitting over here, well, that is not homologous to disk 3 sitting over here and disk 1 and 2 orbiting each other over here. And so, right, what we're going to see is, well, we might not have homology in as high degrees because of this first thing, but in the second case, when we do have homology, we're actually going to have a lot more. And so one final thing I kind of want to note here is there are going to be relations between these various tori, and in the ordered configuration space of points in the plane, this space will kind of look like gluing a bunch of these, I guess, n-1 tori together in various ways. That'll introduce relations on homology, but in general, we're going to have a bunch of n-1 tori. In this case, we want to say, well, are all of the tori that we get by taking products of, say, 1 going around 2 and then maybe a pair of 3 going around 4 everything? And it turns out the answer to that question is no, and that's going to make these spaces a little bit more exotic and a little bit harder to manage. So, right, is this everything? And well, immediately the answer is going to be no, and this is going to be a result of Alpert, Kale, and McPherson again, and then later on built on this by Alpert and Manon. And we'll see this by looking at the complex that we're going to call cell NW. And so what is cell NW? It's going to be a simplicial complex, or a singular complex, and it's going to be a subcomplex of the Salvetti complex. It is a subcomplex of the Salvetti complex of the ordered configuration space of points in the plane. And right, we don't really need to know what this means in a second, but the cells are going to be labeled by ordered partitions of the set 1 through n. And right, it's easiest to see what this actually is through an example. So example, we're going to look at cell 3-2. And it's going to be a space with the following structure. So it's going to look like a hexagon with sides doubled. 1, 2, 3. And we're going to talk about the various classes we're going to see in the homology here. But we're going to label our points by partitions that look like partitions of 1, 2, and 3. And both the order of the terms in the partition and the order of the individual blocks in the partition are going to matter. So here are all of our various 0 cells. 2, 3, 1. 2, 1, 3. And here are all of our various 1 cells. And let's just describe these very quickly. 1, 3, 2, 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 3, 1, 2, 2, 3, 1, 3, 2, 1, 2, 1, 3. Let's be consistent here. 3, 1, 2, 1, 3, and finally 2, 1, 3, and 1, 2, 3. And so, right, we've got this complex over here. We have partitions of 1 through n, right? And if we remove a bar from one of these 0 cells, we're going to get one of the neighboring 1 cells up to possibly reordering the elements inside that block. And so the big thing about this space is, well, it's a result of Alpert, Kale, and McPherson. McPherson, right? McPherson. In 2019, that, well, this cell complex is actually going to be homotopy equivalent in an SN equivariant way to the ordered configuration space of unit diameter disks in the infinite strip of width W. And so, right, what's going on over here? We've got 7 loops in this space, and I'm going to talk about a few of them. So in general, the 1 cells are going to correspond to 1 disk passing over another. So in this case, this 1 cell up here, this is going to correspond to disk 1 sitting to the left of disk 3 and 4, and disk 3 passing over top of disk 2. And in general, we're going to be able to say, okay, that tells us that this loop over here, well, this should really be the loop where 3 and 2 go around each other, 3 and 2 go around each other, and 1 sits all the way over here on the left. So, right, what do we get immediately? Well, if we think about it and we look at these cells, for instance, we'll be able to say, okay, this blue loop down here now, that's going to correspond to 2 and 3 going around each other like this, and 1 sitting on the right. And from this picture, we see, oh yeah, it's clear that these are 2 different classes in homology because, well, there are clearly 2 different circles up here, and there are no ways to get from our red circle to our blue circle. And so we can see very quickly that, right, we have 6 of these types of loops, here, 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 and here. And note, this corresponds to, well, the 3 ways of choosing the pair that orbits each other times the 2 ways of putting the remaining disk on either side of that pair. And so with this in mind, right, we stare at this complex a little bit longer, and we note, well, that doesn't generate all of the homology of the complex. We finally have this kind of inner loop over here, and I'm not going to draw what this loop is, but as compared to the red and blue loops, this is going to be an S1, which, unlike the red and blue loops, which we should think of as 1 tori, so these are both 1 tori over here, we should think of this this purple loop as a 1 sphere. And it's not going to be too important for us now, but I will tell us that, okay, the existence of this purple loop is going to imply that when W is greater than 2, this ordered configuration space of disks in the strip of width W is not going to be a k pi 1. And this is a big difference from all of these other disk point configuration spaces, where at least if you're dealing with points on a surface, they are going to be a k pi 1. Things are nice. Points on higher dimensionals generally lead to various other k pi n, and the world kind of is a nice thing. When we are dealing with width 2, this will actually be a k pi 1 for the braid group that it corresponds to, but we should think of this kind of as a braid group where we no longer have the relation where we can switch and then switch and switch back. That relation doesn't exist. We have to get rid of various things. What this also tells us by looking at our picture, namely from the red and blue, is that, well, the kth homology of the ordered configuration space of n disks in the infinite strip of W is not 0, then this is going to tell us that the kth homology of the space is going to be much bigger in general than the kth homology of the corresponding configuration space of points. So dim HK, ordered configuration space of points in R2. And right, this is because it's a result of Alpert, Kale, and McPherson that this is generally exponential in n, whereas this is just going to be polynomial in n. So, right, we see, okay, these spaces are significantly bigger in terms of their small homology classes, though they don't have the same number of big homology classes, right? In this space, our complex cell 3-2, it's a one-dimensional complex, but as we saw up here, here's a perfectly good 2 class in the ordered configuration space of 3 points in the plane. So, right, we don't have higher homology classes, but we do have an overabundance of these lower homology classes, especially these classes that are going to look like tori. The other thing that this is going to tell us is that, well, if you stare at this complex long enough, then the dimension of cell NW is going to be equal to n minus the ceiling of n over W. And as a nice result of this, so theorem, right, this is a result of Basabe, Gonzalez, Rajak, and Tamaki in, I believe, 2014, that, well, this is going to imply that the topological complexity or the sequential topological complexity of a space is going to be less than the homotopy of dimension of the space, homotopy dim of x times r. And so, right, as a nice corollary to this, we're going to be able to see, well, the topological complexity of the ordered configuration space of n disks in our strip, this thing should be less than or equal to r times n minus the ceiling of n over W. And right, this is the rather standard type of result where we say, oh yeah, we can bound topological complexity by homotopy dimension. But right, as it seems in general, the harder thing to do is get a bound from below. So we ask ourselves, what about a lower bound? And as I said prior, you could try to do something with the cohomology ring of the space. But the cohomology ring of this space is rather complex. I barely understood it when we needed to do second topological complexity or just regular old topological complexity. But instead, we can use an argument kind of expanded upon by Ben Knudsen in a recent paper that uses the fact that there are a lot of disjoint tori in the space. And so in order to deal with this, we're going to use tori. And so what's the idea? Definition. And n and M torus T in Y is homologically decomposable if the inclusion map of T into Y induces an injection on first homology, on the first homology of these two things. So H1 torus into H1 of Y. And we're not going to only need homological decomposable tori, but we're going to need pairs of them. And so we say a pair of M tori T1 and T2 in Y is homologically disjoint if the image in the first homology of the first torus intersect with the image in first homology of the second torus is equal to 0. And so this is all occurring in H1 Y. And so what's going on over here? Well, this is again probably best illustrated by an example, namely the example of these configuration spaces. And so if we go back over here, we say to ourselves, okay, let's copy this space out so we can work with it down here. Well, clearly, red and blue, they're going to be tori in our space. They're homologically decomposable because, well, both of these represent non-trivial classes in homology. And similarly, well, blue and red don't see each other at all. They're disjoint tori in our configuration space. So the world is going to be nice and happy. And as a result of this, we're going to be able to use the following theorem by Ben Knudsen. that was building upon various results using zero coupling product, but kind of made it a little bit simpler, is saying if Y has a disjoint pair of homologically decomposable M tori, then we're going to have that our sequential topological complexity of Y is going to be bigger than R times N. And so it turns out that it's going to be relatively easy for us to find tori. So goal, find disjoint decomposable tori. Find disjoint decomposable tori in this disk configuration space. And well, it turns out that the following is going to work perfectly well for us. All we're going to do, say for an example, and just kind of building off what we've seen before, is, well, these are two tori in the ordered configuration space of 4 disks in the infinite strip of width 2. So right, we've got 2 orbiting 4 and 3 orbiting 1. And similarly, well, we can have 3 orbit 2 and 4 orbit 1. And these tori are going to be disjoint because what happens to the image of these 2 tori? Well, in H1, the image of this tori is going to be the following. It's going to decompose as 4 and 2 are going to be sitting over here, where 3 and 1 orbit each other, along with the direct sum of 4 and 2 orbiting each other, and 3 and 1 sit over here. And well, you can check what happens with the above pair, are 3 and 2 and 4 and 1. Well, it's going to be 2 different things. And it's the result of Alpert and Manin. So Alpert and Manin are going to give us a basis for homology. So Alpert, Manin give basis for the kth homology of this disk configuration space for all n, k, and w, are going to prove that these things are disjoint, if you just look at that basis. So in general, the argument is, say, okay, you're going to make tori like we have up here, and we can make bigger and bigger tori if our width is going to be bigger, but all you're going to do is just start exchanging the topmost label of our disk. So if we have more tori, we just kind of shift everything, the top labels over here in a cyclic way like this. And this is going to define us disjoint tori. And right, this gives us our proof. We found these tori, which are going to be maximal dimensional. And this is going to tell us, okay, now we know these tori are large. So it follows that the R sequential topological complexity of n disks in the infinite strip of width w has to be bigger than R times n minus ceiling of n over w. And because of our other bound, right, we can replace this greater than or equal to with just an equal to. So we have our results. A few things to note. This method of proof does not recover the earlier results of Farber and Yasvinsky or Grant and Gonzalez. So this doesn't work for the ordered configuration space of points in the plane. And this turns out because, well, what's the biggest class? We've got a bunch of points all orbiting each other in concentric circles. You do any of these rearrangements, and it turns out none of those 2 large tori are actually going to be homologically disjoint, though they are all decomposable. And so as I end, I want to point out a few future directions for this, especially because I think some people might be interested in the last one, or I guess the first one, and I'll start this off that way. So I think disks and graphs are something that's rather interesting and kind of continue to build on things we know about graphs, and also building on kind of this real world thing where the configuration space of robots moving along tracks, well, these robots are still going to have some volume. And so I know that a lot of the results that do this use Abrams' model for configuration space, and then use the Farley-Sobolka discrete gradient vector field to look at cohomology. And one thing, a paper that I've kind of seen before, but hasn't actually been published as far as I know, and is only part of a dissertation, is this result by Jimin Kim, who is a student of Matt Kale. And that says if gamma is a tree, then the disk configuration space of n disks in gamma, where we're going to be using the graph metric, this is going to be homotopy equivalent to Abrams configuration space, discrete configuration space for gamma. And so, right, we're not going to be doing any subdivisions here. In fact, you get all of these results, and if you have a few enough robots, you get the classical results for topological complexity for points in a tree. But this will allow you also to see something where now your points have a little bit bigger volume, and your graph gamma is a tree. So this result only works when gamma is a tree, but we do have now a new class of things to think about that now allow us to consider things where rather we don't have just points, but things with volume. Another class of things that I think, as far as my understanding, is still a bit mysterious, are ordered configuration spaces, unordered configuration spaces. So, right, one thing we can say about these unordered disk configuration spaces is the following: unordered disk configuration spaces, and right, these are just going to be the quotient of these ordered disk configuration spaces by the natural symmetric group action that relabels the points. And so I know there was some work done in 2019 by Bianchi and Riccio Mettler, bounding the topological complexity of unordered configuration space of points in the plane, though they weren't able to get a precise bound besides when the number of points is 3. So I ask this question, which at first kind of might seem a little bit harder, but it has at least slightly more of an answer to my knowledge, is what is the topological complexity of the unordered disk configuration spaces in the strip? And it's a result in a paper I'm about to put out, where I'm also publishing these other results, is that, well, if W is equal to 2, and N is odd and greater than or equal to 3, then, well, the topological complexity of these unordered disk configuration spaces in the strip is going to be equal to 2 times N minus the ceiling of N over W. And so this result probably can't use the same technique as this. So this result uses the same technique as this paper, but if we want to generalize to different W and N, that probably won't do. One thing I want to note here, though, is Alpert and Manin work out the cohomology ring of this configuration space for all finite fields. So F, a finite field, F equal to Q, or a finite field. And so you would hope you could do some zero coupling type argument to say, okay, get a better bound here for that. And so with that in mind, I think I'm going to end. Any question?
Thank you very much, Nick. This is a great talk. So are there any questions from the audience?
Yeah, I have a comment and a question.
Yeah.
One is that when Michael Farber was in Durham, he had a student, Kenneth Dealey, who wrote a thesis on these disk configuration spaces on graphs. Yeah. So I don't know if it's available online. I can't remember what was in it, but it might be something to look up. Maybe Michael could send it to you.
I've seen this thing, and I know Matt was talking to me about this a bit because I'm working on him with a separate thing. but he implied that the result of his student Kim covers everything in that earlier paper.
Okay.
She is well aware of this, and I think built upon that quite a bit in order to get this result.
Okay, good. And then the question was, what happens if you replace the strip with an annulus of width W? Do you think it goes down or up?
I would say it most likely goes up, if only by one. I know for a fact one of Fedja Manin's students is working on, I guess, the annulus case, where instead of viewing the annulus as an annulus that looks like this, he's replacing it with, say, an infinite tube, same idea. And he's working out the calculation of both the homology and cohomology groups of this space.
Okay.
And so I know he's assigned that to his student about a year ago. I don't know how it's going along, but I know someone is working on this space in general, if not the topological complexity, though.
Okay, thanks.